The next point on the titration curve we can consider is what's labeled D on the curve. Again, that is our halfway between the two equivalence points. So halfway between equivalence point 1 and 2. So that is when we'll have our concentration of HA minus will be equal to the concentration of H2A. So we'll have our intermediate form plus our fully protonated form. And again, because it's halfway between these two equivalence points, that means half of our reactions happen. That's why these are equal to each other. So again, we can use the Henderson-Hasselbalch equation, pH equals pKa plus log base over acid. This term is going to go to 0, and it's key to note here that this is pKa1 now. So because we have our fully protonated form is the acidic form. So that'll give us a pH that is equal to 5, because that's the value of pKa1. Okay, so again, we could find different points along the curve, but the key is that this is a buffer here. So I'm just picking a point that's easy to calculate. So the final point that we're going to consider, we won't worry about the excess part. We've done that twice already. We won't do it again. Is the second equivalence point. So at the second equivalence point, all of our, what started as our weak base, everything is now H2A. And so we have a weak acid solution. Okay, so we now have our H2A is going to dissociate into HA minus plus H plus, and we want to find that concentration of H plus. So this is similar. We're going to have an altered formal concentration. We've diluted this by quite a bit, and form X and X. So we will use, Ka1 is equal to X squared over F prime minus X. So we need to find what is that final concentration we have here that goes into the F prime. So F prime is going to be equal to, our initial concentration was 0.1 molar, and we'll have our dilution factor. So we started with 10 milliliters. Forgot to mention this, but we can find that the equivalence point is 10 milliliters, as it has been for all the titration examples we've looked at today. So our total volume would be 10 plus 20 milliliters. So the volume at twice the equivalent, at the second equivalence point, is exactly double the volume at the first equivalence point. We haven't changed the number of moles that's present throughout this process. So that's something that will always be true for any titration. So if you want to find the number of moles, you can use either equivalence point. You just have to remember that they're related by exactly double each other. Okay, so that means our final concentration is 0.0333, repeating, molar, and then we can plug this in to as our F prime in this equation. So we'll solve for this. This gives us X, which again in this case is equal to H plus, because now this is an acid. 5.72 times 10 to the minus 4 molar. Again, skipping a bunch of steps here, but steps that you've done before and hopefully at this point know how to do quite well. So you get a pH of 3.24. And then if we keep going, the excess H plus that's getting added by our titration is going to determine the pH after the second equivalence point. We've already done that. The calculation doesn't change for a polyprotic system. Now, one thing I just want to point out when we're looking at polyprotic acids and bases, we can do all these calculations, is that sometimes it's hard to actually find, I got to find my plot, here it is. Sometimes it's hard to actually see the equivalence point. So if we come back to this chart here, on the bottom here, this curve right here, this is a titration for nicotine, which has a ppb value, ppbs that are listed here, 6.15 and 10.85. The second ppb value is quite large, meaning that it's a very weak base at the second equivalence point. And what you see here is that where we should see, this pretty sharp change in pH, here it's much clearer. We get a good change in pH on the first equivalence point, but the second equivalence point, let me just circle it in green here, we don't see a sharp equivalence point here. And this can happen with either the first or second equivalence point. It's not limited to just the second equivalence point. But this happens just because the base is so weak, the pH doesn't change very much. And so you don't get a sharp equivalence point as it says in the figure here. There's no sharp break at the second equivalence point J because the pH is too low. So, and even for our example problem we looked at here, we can see that the change was not nearly as distinct as it was for a particularly strong acid plus strong base, but even for a monoprotic system. And this is generally true for polyprotic systems. Your equivalence points can sort of smear out and be difficult to observe. So it's something to watch out for with polyprotic acid-base titrations.